Welcome to this video lecture series on transportation engineering. In this session, we shall discuss on the Marshall stability test of the bituminous mix design. The Mississippi State Highway Department, it formulated the Marshall stability test, and the test is applicable to the hot mix design of bitumen and aggregate with the maximum size of 2.5 centimeter, and it is widely used in India. There are two major features of this Marshall stability test. First is the stability flow test, and second is the density void analysis. Now in the first case, that is the stability flow test, the test, it is an attempt in order to obtain the optimum binder content, that is the optimum bitumen content for the aggregate mix type and traffic intensities. The apparatus for this test, as you can see in the figure, are the cylindrical mold with the diameter of 10.16 centimeter and 6.35 centimeter of height. Next is the compaction hammer with a weight of 4.54 kg, which will fall from a height of 45.7 centimeters. Third is the sample extractor. Fourth will be the braking head in order to apply load on the periphery of the mold. Then fifth will be the dial gauge in order to measure the deformation. Now the coarse aggregate, the fine aggregate and the filler material, it should be proportioned in a suitable manner so as to be used for the mix design. The gradation of the final mix after blending of the aggregate and filler should be within the specified range as per the Indian Road Congress. Approximately 1200 grams of the mix aggregate and the filler are taken and they are heated to a temperature of 175 to 190 degree Celsius. 3.5 to 4% by weight of the aggregate, the hot bitumen of the temperature 121 to 145 degrees Celsius is then added to this heated aggregate. And the mix is placed in the preheated mold and compacted by the hammer with the 50 number of blows. The aggregate may be added to obtain a compacted thickness of 63.5 plus minus 3 mm size of the specimen. The three samples are to be prepared for the each trial mix, and once the sample has been prepared, it has to be extracted from the mold using the specimen extractor. The specimen's diameter and height are then measured and it is then kept in water bath at 60 degrees Celsius for 30 to 40 minutes. The stability value of the bituminous mix is the maximum load in kg before the specimen sample it fills, whereas the flow value is the corresponding deformation. It should be understood clearly that whenever the sample is placed for its testing, whatever is the maximum load it can bear or at load where it actually fails, that will be taken as the stability value, whereas its corresponding value regarding the deformation, corresponding to the deformation, will be taken as the flow value. Here it should be noted that if the average height of the specimen, if it is not exactly 63.5 mm, then we'll have to apply the correction factor. And the procedure will be repeated for each trial bitumen content, say with an increase of 0.5%. Now, in order to calculate the density void analysis, so here we'll have to know the percentage air voids. The percentage air voids, if they are taken as theoretically with the theoretical specific gravity of the mixture, then percentage of voids, it can be calculated as GT minus GM upon GM, where GT will be the theoretical specific gravity of the mixture, whereas GM will be the mass density of the specimen. Here GT, that is the theoretical specific gravity of the mixture, it can be calculated as 1000 grams of the mixture divided by W1 divided by G1 plus W2 by G2 plus W3 by G3 plus W4 by G4. Here W1 is the percentage by weight of the coarse aggregate in the total mix. W2 is the percentage by weight of the fine aggregate in the total mix. W3 is the percentage by weight of the filler in the total mix, whereas W4, it is the percentage by weight of the bitumen in the total mix. Whereas G1 is the apparent or the actual specific gravity of the coarse aggregate. G2 is the specific gravity of the fine aggregate. G3 is the specific gravity of the filler, and G4 is the specific gravity of the bitumen. So now to calculate the percentage voids in the mineral aggregate, that is VMA. So VMA, it will be equals to VV plus VB, that is VV will be the volume of the air voids in percentage, whereas VB will be equals to the volume of the bitumen in percentage, which will be equals to GM, that is the mass density of the specimen sample, that will be equals to W4 upon G4. Now the percentage of voids filled with the bitumen, we have calculated VMA, now we have to calculate VFB, that is voids, percentage voids filled with bitumen. So VFB will be equals to 100 into VB upon VMA. VB here is the volume of the bitumen and VMA is the voids in the mineral aggregate. So the above values, when they are found for each mix with the different bitumen contents, the graphs are to be plotted with the bitumen content on the x and the y axis. So here basically from the figure we can see the specific gradation of the aggregates for the bituminous concrete surface course. So whatever aggregate that we have taken, here we have referred to 1200 grams of the bitumen, 1200 grams of the aggregate sample. So it should contain all sizes of the aggregate, that means it should be a well graded aggregate so as to fill in the voids present in the larger size aggregates by the smaller size of the aggregates, which will be the coarse aggregate, the fine aggregate, and that the filler. That means the aggregate, the voids present in the coarse aggregate will be filled by the fine aggregate, whereas the voids present in the fine aggregate, they will be filled by the filler material. And still, if there are the air voids remaining in the specimen sample, then it will be filled up with the bitumen. So we'll have to draw in all 5 graphs. First is the Marshall stability test value graph. Second is the flow value graph. Third is the unit weight. Fourth is the percentage voids in the total mix, that is the volume of voids VV. Fifth is the percentage voids filled with the bitumen, that is VFB. Now if you observe the graphs keenly, in the first case for the graph of the Marshall stability value against the percentage bitumen, here we can observe that if there is an increase in the bitumen content, then correspondingly there will be a decrease in the stability of the aggregate mix, and it is due to the increased fluidity in the bituminous mix with the increase in the bitumen content, which is in the liquid state or in the fluid state. In the second graph, if you observe for the flow value, here there is an increase in, if there is an increase in the bitumen, it will help the aggregate mix sample to deform, as the increase in the bitumen will act as a lubricant into the concrete mix. In the third case, with the increase in the unit weight of the aggregate, it will be maximum, that is 100% at the full saturation. That means we know that the unit weight of the aggregate mix, it will be 100% when it is fully saturated. And this full saturation will be obtained when the voids, they will be filled by the bitumen. But if there is an increase in the percentage of bitumen is increased, then as the unit weight will decrease, just because the specific gravity of the bitumen is less than the other materials. That means once the entire specimen sample it is saturated, that means the voids they are being filled up with the bitumen. Still, if there is an increase into the bitumen content in that sample, it will decrease the unit weight, because the unit weight of the bitumen, the specific gravity of the bitumen is less than compared to the other ingredients of the aggregate mix. The next graph is for the percentage voids, that is VMA to the percentage bitumen. Here, increase in the bitumen will decrease the percentage voids in the aggregate mix. As it is clear that if there are voids present in the aggregate mix, then those voids, they will be filled up with the bitumen. Hence, increase in the bitumen will decrease the voids present into the aggregate mixture. And lastly is the graph for the percentage aggregate voids filled by bitumen, that is VFB, by the percentage bitumen. So here, increase in the bitumen will fill the voids in the aggregate mix. Hence, if there is an increase into the bitumen content, it will fill the voids with the help of the bitumen. So in order to calculate the optimum binder content or the optimum bitumen content, we'll have to add the bitumen contents at B1, B2 and B3, where B1 will be the maximum bitumen content in the first graph, that is the corresponding bitumen content for the Marshall stability value, whereas B2 will be the bitumen content at the maximum unit weight or at the maximum saturation or the 100% saturation of the bituminous mix, whereas B3, that is the bitumen content, can be found out at the percentage volume of air voids when they are at 4%, then the corresponding bitumen content has to be taken as B3. So adding the values of B1, B2 and B3 and taking the average of the same, that is B1 plus B2 plus B3 divided by 3, will give us the optimum bitumen content. I hope you must have understood the test. With this, we shall stop. Thank you. These are certain references referred for this particular session.